Welcome to the latest video in your Design of Experiments course. And what this video is all about, of course, is a follow-on from the last lecture, which was all about the 2 to the 5 minus 1 half fraction. So we are going to get into a 5-factor problem now. We're going to explain the problem to you in a moment, but essentially what are we doing? We are trying to control the thrust from a rocket, and we are trying to hit 750. So just before we go to the computer, just a reminder, we're above the red line. So what we're doing here is a straight modeling DOE. So the analysis, which is going to be the marginal means to understand S, and then a regression model to be able to hit Y. Those two techniques all come from one experiment. What we've been doing, of course, in the last couple of exercises is doing the marginal means down here and then doing the modeling with a second experiment. Because this is a smaller experiment, we can do everything from the one experiment. So let's go to the computer, introduce the thrust problem, and then take a look at the analysis. Okay, well, here is the problem. As we mentioned, it's 5 factors. You've got muon flux setting, the phase converter, the antimatter ratio, the phase inducer, and the test pilot. The target we're trying to hit is the thrust coming out of the engine, and we're trying to hit 750. You can see on the right hand side there the current performance. We're hitting 633, and of course we've got far too much standard deviation. If we dropped that red distribution on target, we would still have defective performance, because clearly that red distribution will not fit inside our tolerance lines there, the two red lines. We're trying to be between 775 and 725. So we have to control S and hit the target. So there's our challenge. It's 5 factors. So we're going to use the 2 to the 5 minus 1 half fraction. Let's go to DOE Pro and let's look at that DOE now. So here is the DOE. Now the analysis is the same as we've always done. We're going to do marginal means first to look at S and Y, and then we're going to do the modeling in order to be able to hit the target. So if I go Analyze Design, Marginal Means, and I can go both Y and S, and of course the first thing that comes up is the S marginal means. What we're interested in is the big red signal on the right hand side there, and of course what we need to do is to put the test pilot to 2 to go to the bottom of that line. Let's put that knowledge on the board. Okay, so the S-hat decision. We've gone for pilot to 2. So there's the first piece of knowledge from our DOE analysis. Now let's go back, create the model, and ask the model to hit 750. Now just before we do the modeling part, let's just look at the Y bar marginal means. You can see that the test pilot has a small effect on the thrust, but very little. So that's good news, because we're going to lock off the test pilot. It's not going to have a big effect on our ability to hit the target. So let's go back to the data, Analyze Design, Multiple Response Regression, and we get the first regression table up. Now of course all of these p-values on the right hand side are all black, they're all insignificant. So we're going to deal with the interactions first, and you can see, look, I've taken away all the X's out of those boxes already, and now I can hit regression again, Analyze Design, Regression. Now what I'm left with, of course, is just the main effects, but there's 2 main effects in the middle there, the phase converter and the antimatter ratio. they've also got to go because their p-values are too high. If I do that and regress again, now we end up with the final model. And for this model, of course, we're going to ask the optimizer to hit 750. So if I go in, make sure that the pilot is held to 2, click through that window, drop the menu and go equals to 750, add objective and optimize. It says I can hit 750. I'm going to put those settings in the worksheet. You can see them: 27.6, 30.19, 2.55, 406 and test pilot 2. Okay, so we've put those 5 settings on the board there. There they are. Of course, our prediction is we're going to hit 750. So of course, what we're going to do now, we're going to go back to the simulator. I'm going to dial those settings in and we're going to see what we actually hit. So let's see if the confirmation test confirms the model. Okay, so before, of course, we confirm the model, let's just generate 100 data points for our original performance. There it is. We saw that a little bit earlier. You can see we hit in 633 with a really wide standard deviation. Let's take a picture of that and lose the data. And then we can dial in. Let's have a look. 27 on the mu1 flux, 30.19 for the phase converter, 255. I can only go 2.5 for that. Plasma is 406. Very difficult to hit 406 on the plasma, but I've got that as good as I can. And test pilot 2. And now I'm going to generate 100 and see if I hit 750. There you go, we've hit 755. So a little bit off center, but that might be because it's difficult to dial the actual values in to the control systems that we've got on this simulator. So let's put that on the board. So 750 was the target. We've hit 755. So we're a little bit off center, but partly that's because some of the controls are very difficult to hit. Trying to hit this exact number here is very difficult with the controls that we've got. And this is a really important point. The computer, the system, is telling us that this variable is really important, but we have a really rough and ready control dial on that. It's telling us to spend more money on these control systems. Now, this is the power of DOE. This is process knowledge, because how else would you get this knowledge? It's telling you how to reduce standard deviation. It's telling you how to hit the target, and it's telling you to spend money on this variable right here to change the control system. This is the power of DOE. Process knowledge is pouring out of these tests. No other technique can generate this much knowledge in such a short test window. Now in the next video, what we're going to do, of course, is we're going to move on from single output problems. We're going to look at something a little bit more like real life, where you are trying to model and hit 3 targets at the same time. But that's going to be in the next video. See you next time.